All right, still in 7.6, we're up to 2c. It wants me to take the limit as x approaches 0 from the right-hand side of the cosecant of x to the x. Oh, this isn't going to be good. So again, y is equal to this nonsense. Then we're going to put a natural log in it to get that exponent out. And that's going to turn into the x times the natural log of the cosecant of x, which then the cosecant, as x goes to 0 from the right-hand side, the cosecant, which is the reciprocal of the sine, it's going to infinity. And then I also have, so this is infinity to the 0. So by doing this, now I have 0 times infinity. So now I need to fix that by bringing that x down again. So I have the natural log of the cosecant of x over 1 over x. So now it meets infinity over infinity. So I can use L'Hopital on it. What's the derivative of the natural log function? It is 1 over the junk times the derivative of the junk. The derivative of the cosecant is negative cosecant cotangent. We haven't used that one in a long time. All over negative 1 over x squared. I could wipe out a cosecant. And so I'll have a negative cotangent. Oh, I have a negative on the bottom. The negatives will cancel. So a cotangent of x over a 1 over x squared. Now, if I stick in 0 now, the cotangent of 0, that's an infinity, and the bottom's infinity, so it's infinity over infinity. So now I have to do it again. Now, I could simplify this a little bit without having to do it again. Let's think about this for a minute. I could change cotangent to cosine over sine, and the x squared that's in the denominator's fraction really belongs upstairs. So that would give me that. But we had this nice little rule that said x, the limit as x approaches 0 of x over the sine of x is 1. So I'm going to split this up a little bit and make it x over sine of x times x cosine of x. This piece is going to go to 1. This piece over here is going to go to 0. 1 times 0 is 0. So I have the natural log of y is equal to 0. I have to undo that by putting an e through. So I get y is equal to e to the 0, which is 1. And so the limit is 1. Now we're going to talk about growth rates. Okay, if you're trying to see which function grows faster, you have two functions, f and g. If you take their limit as x goes to infinity, you want to know which function is growing the fastest? If you get g of x over f of x and you get 0, then f grows faster than g because you're dividing the bottom. The bottom's going in with a bigger number, so it's going to make it go to 0. Or, if you write it in reverse, the limit as x goes to infinity and you get f of x over g of x and you end up getting infinity, still f grows faster than g. New thing, if you take the limit as x approaches infinity of f of x over g of x and you actually get a number That means they're growing at comparable rates. Some books say they're growing at equal rates. They're growing at the same rate. That works as long as your m is between 0 and infinity. So let's see. Example 3a. The functions are natural log of x and x to the p being greater than 0. So if I set this up and I take the limit as x goes to infinity of the natural log of x over x to the p, and that would be infinity over infinity, so I'd have to use L'Hopital on it. That would be 1 over x over, now the derivative here is p, x to the p minus 1, because p is a number. If I simplify that, that turns into 1 over, okay, it's going to be p, x to the p again, because the 1 over x belongs on the bottom. And as x goes to infinity, this is going to 0. If it's going to 0, then we know the 1 on the bottom is growing faster. So we're going to say that g of x equaling x to the p grows faster, which means that any function that has x to a power, where power is positive, is going to grow faster than the natural log function. Part B, let's squeeze it over here. F of x is natural log to the q of x. And g of x is x to the p. As long as p is greater than 0 and q is greater than 0. So if we set it up the way we've been setting these up, this is going to be the limit as x goes to infinity, natural log to the q of x over x to the p. And we're going to do a little bit of mathematical gymnastics here. We're going to rewrite that as the natural log of x over x to the p over q all to the q. Because when you raise the powers, you multiply, and that would take it back to the original. However, we already know that this little piece let me rewrite it again. We could take the limit as x approaches infinity of the natural log of x over x to the p over q and raise the whole thing to the q. That won't change it any. So, but we already know that from part A, the natural log function grows slower than any x to a positive power. Now, since p and q are both positive, this is going to be a positive power, so this little guy is going to go to 0, by example, part A, and 0 to the q is just going to be 0. So this whole limit is going to be 0. Which then means that the denominator grows faster, so now we can also say positive powers of x grow faster than positive powers of natural log of x. The x to the p grows faster than the natural log of x. Natural log to the q of x. So these are two really good ones. X to the p, x to any positive power is going to grow faster than any power of a natural log function. If you think about the natural log function, it grows really, really slowly when you graph it. So that would make sense that x to a power was going to grow faster.